Hello, today's video will be over CFD pipe flow analysis. Before we look at our simulation results, I wanted to briefly introduce what computational fluid dynamics actually is and why it's a valuable tool for engineers. CFD is a numerical method that solves the governing equations of fluid motion across a 3D geometry. Instead of relying only on simplified equations or approximations, CFD allows us to simulate detailed flow behavior throughout an entire system. What makes CFD so powerful is that it can capture effects like turbulence, flow separation, mixing, pressure changes, and energy losses that would be very difficult to measure experimentally or calculate by hand. In engineering design, CFD plays a major role because it gives us early insight in the developmental process. It helps us answer questions like, where are the high velocity regions in the system? Where is the pressure dropping the most? And how does turbulence behave through elbows, reducers, or complex transitions? CFD allows us to test multiple design variations rapidly without needing to fabricate physical prototypes. It reduces cost, shortens developmental time, and enhances our ability to predict real-world performance. It's especially valuable in cases where experiments would be expensive, risky, or difficult, like internal flows, high-speed flows, or systems with many components. So overall, CFD is not just a visualization tool, it is a predictive tool that supports better engineering decisions. Pipe flow is a classic example of CFD where CFD can be extremely useful. Yes, we have well-established hand calculation methods, but real-world piping systems are rarely ideal. They include sharp or sudden diameter reductions, long radius or short radius elbows, varying surface roughnesses, turbulence in secondary flows, or flow separation at fittings. All of these effects introduce uncertainty when using manual correlations. CFD can help us visualize these losses directly by computing the velocity field and the pressure field throughout the system. It shows us how the flow actually behaves, not just how we assume it behaves. For our pipe system, we included several different types of components to make the problem more realistic and more interesting. We begin with a straight section of 2-inch diameter pipe that is 6 inches long. Following, the pipe suddenly contracts to 1.75 inches for 4 inches of length, then suddenly expands back to 2 inches for another 6 inches of run. From there, it enters a long radius 90-degree elbow that runs 6 inches vertically upwards, then passes through a second 90-degree elbow to return to horizontal flow. And after that, we repeat the same reducer, short pipe, expander pattern on the outlet side. So in total, we have 4 different sudden diameter changes, 2 elbows, multiple straight sections, and a realistic surface roughness. So this gives us a good challenge, because the flow will be fully turbulent and it will experience a combination of major and minor losses.
All right, hello everybody. Today I will be showing y'all how to calculate pressure drop over a piping system and also uh, just how to evaluate results from a CFD simulation. So I started with a discovery model. As you can see here, all I did was pull some different circles I drew or sketched, and I created this array of piping components or spools. I have 2 elbows, and then I simulated 2 sudden expansions that would be due to like a valve or anything else on this pipe. Um, None of these numbers are directly, associated to um, piping schedule or anything like that, but they this will suffice for the exercise today. And from there, oh, and also I wanted to take mention this. There are ways to, if you have a piping system, like let's say you have it from SolidWorks or whatnot, and you want to pull the fluid domain as what's shown here, You can go to the prepare tab and I think it's prepare. Yes, volume extract. You can use this tool. There's many good videos online that you can follow to use this tool effectively for already a solid portion of a piping system if you want to extract the fluid domain to make it more computationally cheap to run. But as I mentioned before, I'm going to show you the process to do this, and today I'll be using the Fluent meshing analysis system to do this. And I'm just going to walk through how I would do this. So first, we make sure our geometry imported from the Workbench workflow, and it has for me. And then for local sizing, since we maybe could use some refinement in these elbows, but for this exercise, I don't think it's necessary. There are good videos on how to add local sizing with this software, but I will not show it in this video. And then we are working in meters on this mesh, and so I need to size this down a little bit. So minimum size, this is going to be the smallest uh, global sizing in this piping, and then max is going to be obviously the max size. So let's play around with this a little bit and see if we can get something that looks a little bit better. I think we still need to go a little bit smaller. And then let's see. Honestly, that's probably good. And then I'm also going to change the curvature normal angle to something a little bit lower, like 12. That adds more refinement on curved sections, and I think it would add a lot of good detail to this mesh. So we're going to generate the mesh and let it load. Might take a little bit. All right, that looks good for what we need it for. Now we're going to describe uh, this mesh that we're meshing right now. This is only a fluid region and there are no pockets or anything inside, so I will select this. And then just for simplicity, we're going to keep these all as no. And then also in Discovery, forgot to mention, but I did create some name selections for the inlet, outlet, and then the wall region. And this is important to do before we go into fluent meshing because it makes assigning the boundary conditions much easier. And we're going to do a simple one today. We're just going to do a velocity, inlet, pressure outlet, and the wall region. So let's update the boundaries. And then this is asking for all of this mesh, is it going to be a fluid in these cell zones? And in this case, since we're not modeling any solid part of the piping, it would just remain fluid. All right, and then for this, I would like to have some boundary layers just because for any piping system, you want to see what's going on closest to the wall. But I believe these settings are good. I just up the amount of layers. Okay, and then this will take the longest to load up. But what I like to do, see, this is max cell length. So I like to see what I have for my max cell length, 0.005, and have that for this. I don't think it really does anything, but I feel like it does. Okay, now that the mesh is generated, we can kind of look at it and see if this is what we want. We're not doing anything, too crazy. If you're doing this for a really intricate system or maybe some kind of volatile fluid, like or compressible fluid, you might need some more refinement than this. But this is quite good. We ended out with 70,000 cells, and I think for the purposes today, this will be okay. And I will discuss more how to validate these results later, because potentially maybe this isn't enough mesh, but we can find that out later. Good practice is to perform a mesh check. You're just looking for error codes in the console, and I don't see any. Also see the quality. All right, and these numbers are good. So next step, let's go into solution mode. This is just making sure that you did the checks that we just did. All right. Now that Fluent has opened, we can now proceed with solving the solution. For simplicity, I already went through and put in everything and solved this out, so we didn't have to wait for it to solve together, but I will go through each step that I changed. So we start with this general page. Since we're going to be working with water and it's an incompressible fluid, we can do the pressure-based solver type, which is default. We're going to keep it a steady state since nothing should be changing over time. And then just to accurately represent this in, in Fluent, I did load in the gravitational acceleration into this model. And then it's best practice generally to, go down this list in order, just because what you pick here will change the material import. Um, but just going off of that, we're going to keep energy equation off, which is default, and then we're going to change our viscous model. It was at K omega. We're going to go to K epsilon. We're going to do realizable, and then with standard wall function, K epsilon realizable is a good robust model for most cases, or at least most simple cases. Of course, the more detailed you need to get, you may need to change this around a little bit. And then I'm using standard wall functions in order to put in our pipe roughness later. So going from there, that should be everything for the models part. Next, we wanted to add in our liquid water into our simulation. So default is just air. So I had to add in water into my simulation. So I went to the Fluent database here. I scrolled down, selected water, hit copy, and then once I hit copy, it put it into the scene. All right. And then from there, like I said, I've already solved this out, so all this has been done, but I'm just showing you how you would do it. So we need to assign the cell zone in the region that we're working with. Default, it's air. So if we go to the cell zones conditions and we double click our solid, which is the fluid region for us, we just go to this drop down and click the material we want there. I want water, so I put it there. And then for boundary conditions, I did forget to mention this, but before you select your model, make sure that your flow is truly turbulent and or laminar, because that will change everything in your calculation. I did the Reynolds number calculation. It was above 4,000, so that's why I selected the turbulent model. But if you're using, a lower velocity, you may have a laminar flow. But for the boundary conditions, I'm doing a velocity inlet, and I put 10 feet per second as my velocity. And then for the hydraulic diameter, also I changed this from intensity and viscosity ratio, I believe, and I put it to hydraulic diameter, just because for piping systems, what I've read, this works quite well. And then also, just so it doesn't get confusing, when we were doing the meshing, I did work in meters, but whenever I built this in Discovery, and I live in America, so we're going to use imperial units for this. So that's why we're in imperial units now. And then for the pressure outlet, we don't need to change anything here except for this turbulence method. And we can do the same as the inlet because it's matching inlet and outlet. All right, and then for the wall, if you go on any kind of, or if you go online and you look up, rough pipe roughness for the material you have, you can find different charts and different values for what you're looking for. And I'm doing stainless steel, or that's what I'm going to simulate for. And roughness in inches for stainless steel is about this value. So I put that into my model, and then none of these I changed, but there are functions for each of these, and you may need to use it depending on your case. But I will not cover that in this video. For methods, uh, I put second order upwind for both of these. Default for me, they were first order upwind, and second order just a little bit more detailed, a little bit more robust. So that's what I used. Controls, I didn't change anything. And then for report definitions, I did create this report. Uh, so for you, if you wanted to create one, you would click new right here, surface report, area weighted average, and then it would bring you to a screen like this. And I want to see what the inlet pressure is as the simulation goes on with each iteration. So I, change the name, make sure that it's something that you can look back on and make sense of. If you just leave it as the default name, might not be intuitive what it is. And because I have a pressure outlet set, that outlet is not going to change, but the inlet will. So I set this to inlet. So it's going to be calculating the pressure at the inlet as each iteration goes on. And that's a good way to tell if your uh, uh, simulation is robust, if it actually gets a constant value after a while. And then for monitors, this is just one of my professors normally get me to do this, where we add just a good amount of accuracy to these. The smaller the number, the more it has to iterate to get to this number. Sometimes it doesn't actually get this low, but this just makes it where the simulation will run and just try to get to the lowest value possible, which makes it more um, accurate. So I lowered these from the default value, I think 0.001. All right. And then from there, we need to initialize our um, simulation. I typically use hybrid initialization simply because it's a little bit better than standard for most applications. And all this initialization does is just it starts off your simulation to where um, it solves out faster. And then I ran my calculation. I did 500 iterations, depending on the case you made it add more. Um, but this was a good value for me. And then from there, I obtained my results. It solved out, and this is how my residuals looked. As you can see, we got to about 200 iterations, and then it just flatlined, which means that it's no longer changing as this iterates further, which is a pretty good tell that this is, a decent model. And uh, inherently, CFD is full of error. I mean, it's a computer-based. It's a computer trying to solve a real-life application, and it's solely dependent on what you put in. What you put in is what you're going to get out. So, just because this is flat does not mean it's necessarily 100% true. More testing in the field and/or refinement of your mesh is needed to really validate your results. And so this is my residuals, and then this is that pressure report that I showed. So uh, as you can see, it flatlined too. And I did forget to mention this, but if we go to the physics page and operating conditions, I did put an operating pressure of 20 psi. Default, it's atmospheric pressure. I just wanted to add a little bit more just to make it a little bit more dynamic. So that is the pressure, the constant pressure throughout this system. All right, and then let's go look at a pressure contour of this. So I did forget to mention this too. If we go to results, we can create a plane that intersects the pipe so we can see the cross section of it. And that's what I did previously. So this pressure contour, the surface it's applied to is the plane that I created off screen. Uh, so if we take a look here, we can see this is kind of what we expected. We expect the pressure to drop whenever the diameter decreases. And I mean, whenever any kind of fluid hits a bend, it creates turbulence and also, increases pressure in that region because the fluid is slamming in that area. And like I said right here, pressure does drop right here, which is expected. Uh, I'll explain these numbers a little bit more in a little bit. And then I also created some vectors for the velocity just to see how it looks on the inside. And the inverse was true, and it looks like it's working as expected here too. We decrease the diameter and velocity increases. Pressure drops, and then velocity increases in this region. So that is accurate to what we expect. And then you can see velocity is quite slow right here, just because it's finding the path of least resistance and, trying to find its way out. And if you remember too, the pressure was high in this region for both the top and bottom, so this makes sense. All right. And then a good way to tell if you're going in the right direction, or if the simulation is, at least somewhat correct, is doing a mass flow uh, check. So you would go to flux reports down here, select inlet outlet, compute it, and then as you can see, this net result, or this difference between these two, is very, very small. So that shows that uh, uh, the calculation is good. You want these two to be almost the same number, because whatever you put in, you should be getting out. But because it's a computer-based solver, will be error inherently built into it. And then let's look at the pressure drop. So if we go to the surface integrals right here, you can do area weighted average, or you can do mass weighted. I'm honestly, I still don't have the best method completely understood yet, but typically I've been using area weighted average. Uh, we'll look at both. But if we select the inlet outlet, because that's what we want to see, the drop over these two faces, if we compute it, we get this value right here in the console. So it's saying that at the inlet, we start with this higher pressure, and then at the outlet we go to 0. That's not necessarily true. It's just Fluent works a little bit differently than what you would expect, I guess. Because I loaded in that operating pressure, when it says 0 here, it really means 20. It means that at the outlet we get to that 20 psi, because we have a pressure outlet it's set to that. So it's going to do whatever. It's going to change the inlet to fit uh, that pressure value. So the inlet is really, I guess, 21.587, 6. So we have a pressure drop of about 1.58. So uh, that's our pressure drop right there. And then let's go ahead and look at the mass weighted average, just to see if it really comes out to anything different. And no, it's the same. Uh, both are the same. So I guess, do your own research and see if you can find out what works better for your case. But it looks like for this case, they're both solve out to be the same. And then there are more visualization and also ways to calculate, the values you want. But for the case of this video, that's what we wanted to see, was the pressure drop. Uh, but yeah, thank y'all very much for watching this section of the video.
So with the simulation results, I did some hand calculations so we could try to verify the results and see how accurate our CFD analysis was. So for the hand calculations, I first determined the mass flow rate using continuity, which gave about 6.17 kilograms per second, which is very close to what the CFD produced. Using the pipe diameters, I calculated the velocities in each section along with the Reynolds number and then the friction factors for each pipe diameter. We included both major losses from the straight pipe friction and minor losses from the elbows, sudden contractions and expansions, matching the same components in the CFD model. So for the major losses of the system, we multiplied the friction factor by the length divided by diameter times 1/2 times density times velocity squared. This gives us a total major loss of 0.961 psi. For the minor losses, we multiplied 1/2 by density times velocity squared times the loss coefficients total, so K total. So, and for the total minor losses, we got a value of 0.53 psi. So for the overall system, we got a total pressure drop of 1.19 psi from the hand calculations. From the CFD simulation, the predicted pressure drop across the entire pipe system was 1.58 psi. So that gives us about a difference of 25%. So for a system like this with multiple fittings and strong turbulent flow, the level of difference is completely normal and well within are acceptable engineering limits. CFD accurately depends on many factors, including the mesh, the mathematical model, and the boundary conditions. One of the most important steps in CFD is the mesh independence study, where you refine the mesh and confirm that the solution no longer changes significantly. If the mesh is too coarse, especially near walls, reducers, or elbows, the simulation may underpredict or overpredict losses. Another factor is the turbulence model. In our case, we use the realizable K epsilon model with standard wall functions. This is a good general purpose model, but different turbulence models produce different results. In some cases, switching turbulence models can change pressure drop predictions by 15 to 20%. Boundary conditions also matter. The inlet velocity must be accurate, and the outlet pressure must be defined correctly, and the roughness model must also match the physical pipe. Even small decisions in roughness or viscosity can cause noticeable differences. So overall, CFD is only as accurate as the inputs and assumptions that we make. That'll be it for our project. I hope you guys learned something, and thank you for listening.